All right, class, we're going to get started. Okay, so today we're going to go over, we have two sets of lecture notes today, lecture 9 and lecture 10. Lecture 10 is pretty short though, so we should be able to get through both today. Before I begin as well, I just have two announcements. I made these announcements on Canvas, but I just wanted to make them in class as well, concerning homework 6 and quiz 6. So homework 6 I should have given it out last Wednesday and it would have been due tomorrow night. Instead, I gave it out over the weekend, which is not enough time really for your, I understand many of you are probably starting it over the weekend or early in the week, but I like to give you more time than that. So homework 6 will be, homework 6 will not affect your grade. So homework 6 will not count against one of the two dropped homeworks, and the score on homework 6 will not count into the score on your grade. So I still posted it up there. You'll notice that it's listed as 0 points to reflect the fact that, again, it's not going to factor into grades either positively or negatively. But it's really there for practice. The reason I posted it anyway is, again, for practice, and so that then the TAs will grade homework 6 or score homework 6, so you can get feedback on how to solve the problem types that are covered in homework 6. Okay. Any questions on that, on homework 6? Okay. So, and I think I said this at the beginning, but the homeworks are mainly meant as practice for you anyway, practicing the concepts anyway. It's just it's exactly what the case is for homework 6. So for quiz 6 was originally scheduled for the day before Thanksgiving. I thought the day before Thanksgiving at 3 o'clock is a bad time to have a quiz. So I moved that to the Monday before. Okay, so now it's Monday of that week. And then for that lecture, which is again the day before Thanksgiving at 3 o'clock, I'm going to make that lecture a Zoom/recorded lecture. So I will lecture at 3 o'clock, but that lecture will be on Zoom. I'll send out a link just before we get there. It'll also be recorded as usual, so the lecture will be available on YouTube afterwards if you're traveling or something at that time. Okay. Any questions about that? Okay. All right. So today we're going to get into, again, lecture notes 9 and 10 about hypothesis testing and uncertainty. And at the end, I'll have a note for you we'll talk a little bit about significant digits, because on your quizzes up so far, I haven't been taking off points for significant digits in your answers, because we haven't really talked about, or in depth, we haven't really talked about uncertainty. But significant digits communicate actually quite a bit about your uncertainty in the answer. And so from here on, I will be taking points off basically if you give an incorrect number of significant digits or a wildly incorrect number of significant digits on your answers. Yeah, go ahead. You've lost points on the quiz? If you have, submit a regrade request on Gradescope, and I'll take a look at it. There's a possibility of losing it for a rounding error. So if you incorrectly rounded the answer and it resulted in an incorrect answer, then I believe I took off points for that on some of the quizzes. But if you gave too few or too many significant digits, I did not. And if it was correctly rounded, I did not. On the homeworks, yep. The TAs did say that they were going to take off points on the homework for significant digits. I think I'm going to leave that as is, or else it would cause them to have to regrade everything. So it depends. So significant digits depend. So we've talked a little bit about uncertainty already. So if I say, right, let's say we're talking about the average height of students at the University of Utah, right? And I take a sample of 10 students, and I end up with a result of, I don't know, 70 inches. And I report the result as I got an answer of 70 inches as the average height. And then I someone else takes the same measurements and they report their results as 70.10325 inches as the average height. Those communicate two different things, right? If I say 70, right, without any digits after the decimal, I'm implying that my answer, that number implies that my answer is uncertain to within, I don't know, an inch or a few inches. But if I report the answer as 70.10536, that implies that I'm certain about the answer to 4 or 5 decimal places. So, and thinking about uncertainty, we've already talked about uncertainty, confidence intervals, right? If my proper confidence interval on that height is plus or minus 1.2 inches, right? So if the real answer with uncertainty, with confidence intervals, is 70 inches plus or minus 1.2, then it is incorrect to report it as 70.153026 plus or minus 1.2. That just doesn't make sense. Okay, you're giving far too many digits. You're giving far more digits than are reasonably representative of what the answer is. Does that make sense? So in general, when we're talking about significant digits, the number of significant digits you have should reflect the uncertainty in your answer. So if my uncertainty were 1.2 inches, then 70.1 might be a reasonable answer for the average height. 70.125 would not be. Okay, does that make sense? So they should, so the significant digits that you give your result to reflects your uncertainty in that result. And this is important. As engineers, you will be asked to do analyses, right? You'll be asked to run calculations about, about different processes or about, different real world scenarios, right? If you're doing an internship this summer, this may be one of your tasks, right? To run some calculations. But if you return those calculations to the precision of your calculator or to 6 significant digits after the decimal, then somebody reading the results of your calculation may falsely assume that you believe your result to that many digits. And that's probably not true. And as an engineer, that's probably not responsible, right? So one of the things, and one of the reasons why statistics is part of engineering, why statistics is part of what we require in chemical engineering, is that in many cases, as an engineer, reporting the result of your analysis or reporting the uncertainty in your analysis may be just as important as reporting the result of your analysis. So communicating uncertainty, communicating how precisely you know the answer is critical, right? There's a big difference. If I say the pressure, the maximum pressure that we expect to see as a result of this reaction is 200 pascals. That's very different than if I say the maximum pressure we expect to see is 199.92567 pascals. Those are two different answers. They are approximately the same. They round to the same number, right? You may receive credit for both in a class, in one of your classes, but they communicate two different things. One says, if I report the answer as 200 pascals, then that implies I'm really not so certain, maybe to within 10 pascals or so. And so if you're trying to size a pressure relief valve, you better give me some margin on that 200 pascals. The other result, 199.9256, implies that I know that answer to multiple decimal places. You could size a relief valve to 201 pascals, 200 pascals, and I'm pretty sure that it's going to be okay. Those are two different results. So uncertainty is important and critical as an engineer. And that's, again, gets back to why you're in this class in the first place. And so from here on your exams, I expect to see significant digits that roughly reflect the uncertainty in your answer. Does that make sense?
So typically,
Yeah, within one. So within one or so, right? So plus or minus one. So there's a range of probably 3 or so significant figures that I would accept on an answer without without error. But I have seen, on exams so far, on quizzes so far, I've seen people giving me significant digits out to whatever's displayed on their calculator. Okay, that communicates an improper degree of certainty in your answer. Okay, and as engineers, again, the uncertainty in your answer is in many cases going to be just as important as the answer itself. And in statistics, now we have the tools to discuss that and to understand that. And so from here on, that's going to be something that I'm looking for. Okay, does that make sense? Yeah. Okay. And so you asked me how many significant digits should I show, and the answer is it depends. Okay, and so it should reflect your uncertainty in the answer. Okay, so today again we're going to talk about hypothesis testing, and then we'll talk a little bit about uncertainty and propagation of uncertainty. We'll get back again to maybe some people's least favorite question from quiz 1 and 2 about propagation of uncertainty when we had a linear combination of variables, and we're going to extend that to when we have a nonlinear combination of variables. But we'll get to that in the lecture 10 notes. But first, we're going to talk about hypothesis testing, and this is where we get into. We talked a little bit about this in the last lecture, but we'll be a little bit more specific about it this time. And this is where we're going to get into trying to answer questions probabilistically using what we know about probability, but also distributions and summary statistics about that we can compute. So the major idea of hypothesis testing is trying to answer the question of whether a set of results could have occurred by chance. Another way of phrasing this is how significant are the results. So we're going to come back to this example here, and I believe this is code that we saw in lecture 8 as well. And we've seen this example now multiple times. But this is our emission rate example, where we suppose that the permitted emission rate of some pollutant is 75 kilograms per hour, and 3 values are measured: 72.7, 73.9, and 74.2. Right. So again, this is an example where we're going to say that maybe these measurements are very expensive or difficult to take, and so we only have 3 measurements available. So what we want to know is, so we looked at what the best estimate of the emission rate was, and we said that that was just the mean of those results. But now we're getting into questions of how confident we can be that the emission rate is actually being met, and probability related to that is a probability the emission rate is greater than 75 kilograms per hour. And so again, we're using NumPy and SciPy. So we define our results. We're defining the significance level of 0.05, or 1 minus alpha is the confidence level. And again, we define the limit as 75. All right, so that's what we're testing against. We're testing whether or not this set of results could come from a process that has a mean greater than that limit. This function defines this function. This is a custom function written into this Jupyter notebook that defines or essentially calculates a number of the summary statistics that we've discussed in previous lectures, right? So including the mean, the standard deviation. The standard error is that standard deviation divided by the square root of the number of samples. So the standard deviation divided by, in this case, the square root of 3. We looked at the, for the t-distribution, we said that the t-distribution is parameterized by the number of degrees of freedom. So basically, the more measurements that we make, the narrower the t-distribution gets, and the closer it becomes to the normal distribution. In this case, and the degrees of freedom for the t-distribution, just as a reminder, is n, the number of measurements, minus 1. So in this case, degrees of freedom, n minus 1 is 2. And so from that, we compute again, we looked at this last time, or we looked at this when we looked at the t-distribution, where we then compute the the value of the t statistic that would satisfy that alpha is equal to 0.05. And again, we discussed how we can use that to look at margins of error or confidence on this result. So it would be t star times that standard error. And then we can compute our confidence intervals, and then the limits that we would have on the t statistic, which is something we're going to discuss in just a second here. So when we run that on our results, we can see the expected results. We've been growing this list of statistics that we compute from this example as we go piecewise through the lectures. So we saw the mean is 73.6, standard deviation 0.79. Our 95% confidence interval on the mean, 71.6 to 75.6 kilograms per hour. So this would be an appropriate, a reasonable number of significant digits to use here. You could actually probably report this as 72 to 76 or 71.6 to 75.6. That's reasonable as well. But 71.638 would not be appropriate in this case, right? Because again, our uncertainty is within a few kilograms per hour. And we said this last time. So based on the t distribution, we computed the probability that the emission rate exceeds the limit as 0.046. Based on the area under the t distribution curve, we ended up with this value of 0.046, meaning that there is only about 4.6% chance that we would see results, the results that we saw, again, with a mean of 73.6, and that standard deviation of 0.79. So there's a very low chance that we get those results with an actual mean that's greater than 75, right? So again, this is what we looked at last time. So we're 95% confidence that the population mean falls within this particular interval. And we conclude that there's a slight chance that the actual emission rate exceeds the 75 kilograms per hour. So again, we can write the confidence interval on this data as we're going to say that we expect that the mean is the sample mean plus or minus that t statistic times the standard error, where we're computing that t statistic, again, based on the degrees of freedom of the experiment, n-1. And in this case, since it's a double-sided confidence interval, we had to use alpha over 2. So this was the t statistic value for, in this case, 0.025. And again, this is what our standard error is, the standard deviation divided by square root of n. So, and all of that is something that we've seen before on this example. But now we can reframe this as a hypothesis test based on this problem. And this is a common way of addressing this kind of question or framing this kind of question in statistics. And so we're going to reframe this as a hypothesis test. We're going to see that a lot of what we have up above is going to appear again. So we're going to now say that our limiting mean, mu naught, is going to be equal to the limit that we're trying to test against of 75 kilograms per hour. So in this case, this is the lowest limit of the mean of the actual population, for which we would say that we are meeting the requirements of these emissions, right? So our mean has to be 75 kilograms per hour or lower. And so we're using this as the critical value that we're trying to assess using our t statistic. And the way that we normally frame hypothesis testing in statistics is in terms of the null hypothesis and the alternate hypothesis. And this nomenclature can be a little bit confusing. So we're going to see it through a couple of examples here. And then again, you'll have practice on your homework on this kind of thing, but this is something to pay attention to. So in sort of statistics hypothesis testing language, the alternate hypothesis is typically the thing that we're actually testing for. So in this case, the alternate hypothesis is that the actual population mean is less than this limiting population mean, or this limiting value. Okay. And this is, again, typically the claim to be established. In this case, this is the thing that we're trying to test. Right? We're trying to show, we're trying to see if the mean is less than this limiting mean. The null hypothesis, this is, this would mean that the claim is being denied. So for example, if the mean is equal to that 75 kilograms per hour, or if there's a high probability that the mean is actually equal to that 75 kilograms per hour, then we're going to say that we're going to deny the claim. Yeah. Yeah, I mean, so we'll look at what the distribution ends up looking like when we plot this. But the we're going to start with the. So we test against the most likely way to fail the significance test. So we have, so for example, here we have a mean of 73.6, right? And we're trying to see basically if we could get that result with a mean of 73.6 with these three specific measurements. If we can get that result, even though the actual mean of the actual test is 75 or greater, right? And there's the greatest chance of failing this statistical test if we set the mean, the limit or the population mean, we're testing against the population mean equal to 75 kilograms per hour. So we'll always, for example, get a lower probability if we use a higher number here. Does that make sense? So this is the limiting case. This is kind of like the. It's the most likely case of failing, basically. Yeah, 75 is the most likely case of failing. So if we, for example, if we failed at 76, right? If we set this equal to 76 and we failed that test, then we would definitely have also failed the test for 75, right? But if we failed for 75, we're not necessarily going to fail for 76, right? But since we're actually interested in this limit of 75, we're going to set it equal to the null hypothesis is going to be just that the mean is equal to this limit of 75. Does that make sense? Okay. And we'll see null hypothesis has a meaning in terms of the way we define the t distribution. We'll see that in just a second. This, again, this set of code runs through the calculations for evaluating the null hypothesis. But the key here is that we're going to compute again, we're computing the t distribution, but now you can see we're computing two different values of the t distribution. One is the value of the t distribution for my limiting something. Actually, sorry, there's a mistake here. I was editing this earlier. This should be mean ER minus E limit. Apologies. Sorry. So we have two different values of the t statistics shown here. One is t alpha. So this is the value of the t statistic for our defined alpha value, in this case, that 0.05. And so we can think of this as like how far away from the center of the t distribution we would need to be in order to fail our test. And we have our t limit value here as this is the value of the t statistic that we actually get when we plug in the observed mean. So how far away our observed mean is away from the center of the t distribution. And from that, we can estimate our p-value. So from our actual observed value of the t statistic, we estimate the p-value. In this case, it's 0.0463. And so when we visualize this, apologies, this is a sketch that I made earlier today as I was trying to work through explaining this, but I'll walk you through the sketch. So this is showing just a sketch of what the t distribution looks like and what we're actually doing when we do t hypothesis testing using the t distribution. So we're going to set up a t distribution, in this case, with degrees of freedom equal to n minus 1 is equal to 2. So again, this is going to be a pretty broad distribution. Remember, the t distribution is broader than the normal distribution and gets narrower and approaches the normal distribution as the number of degrees of freedom increases, and basically becomes the normal distribution when n is about greater than 30 or so. In this case, degrees of freedom is just 2, so the t distribution is very different from the normal. And so what we're doing here is we're basically setting up a t distribution curve centered at the value that I'm testing against, centered at that mu naught, centered at that null hypothesis 75, or in this case, value of 75 kilograms per hour, right? So it's centered, we're basically constructing a t distribution, right? A PDF from the t distribution that's centered at the value that I'm testing against, centered at the null hypothesis. And then my t alpha value is the value of the t statistic at which I have alpha, in this case 5%, of the area under this curve, right? So it's the value of the t statistic at which I at 5% of the total area under this curve. And then what I'm doing, so that's my t alpha, and I can write when I compute t. So one note here is that when I compute my t alpha using the t statistic, I end up with a positive number. But in this case, I'm testing. What I want to know is whether my mean is lower. My actual mean is lower than the limit, and so I have to look at minus t alpha, which is going to be somewhere right around here. And then I computed the t statistic for the actual observed, experimentally observed results, and I saw that my actual result was 73.6. And so I compute the t statistic corresponding to the 73.6 and the given standard error of my result. And I saw that the area under that curve was 0.046, right? So we interpreted that last time as there's a probability of about 4.6% that I observed this mean, and the actual population mean is 75. And in this case, what I see is that or my hypothesis test is asking basically, is this t statistic that I computed for my actual experimental results further away from the mean than my limiting t statistic? If that's true, then I have 95% confidence that the actual population mean is less than 75. So put another way, this t distribution, right, that I've constructed, centered at this null hypothesis mean of 75. It's basically answering the question of like, what is the probability that I have if the true mean is 75, right? So again, that's my null hypothesis. So if the true mean is 75, what's the probability that I run a set of experiments and get a computed mean of a certain number or within a certain range? That's what my PDF, that's what my t statistic PDF tells me. And so in this case, what it's telling me is that for a mean of 73.6, right, to see this mean of 73.6, there's only a 4.6% chance of seeing a mean of 73.6 if my actual population mean is 75. Does that make sense? So Therefore, it's not terribly likely that my actual mean is 75. It's more likely that my actual mean is lower than 75. And I can say with greater than 95% confidence that my actual mean, my actual population mean, is probably less than 75. Does that make sense? Yeah, go ahead.
Is it 4.6%?
Yeah, it's 73.6. It's 73.6 or less. That's correct. Yeah, that is correct. So in general, when we're doing hypothesis testing, we reject the null hypothesis if the p-value is less than alpha. So in this case, my alpha was 0.05, right? So this was my t-statistic that I would compute for my alpha of 0.05. And we're going to reject the null hypothesis if the p-value, in this case 0.046, is less than 0.05. So we're going to say to greater than 95% confidence that, and greater than 5% significance, or sorry, less than 5% significance. We're going to say that, or better than 5% significance, we are going to reject that null hypothesis. Here we can see why we set it at 75 and not something greater than 75, right? If I were to take this whole curve and shift it over, right, to 76 or something, then the area under the curve up to this 73.6 would be even lower, right? So think of it another way. It means if I were testing against the null hypothesis that the mean of the population, the true mean of the population is 76, there's an even lower probability that I observed a mean of 73.6 or lower. So this is my limiting case. This is the most difficult test essentially to pass. And so this is the value that I use. Yeah.
So we're rejecting null, that means that our true mean is less than 75.
That means that yes, we with 95%. So we're getting into these statements of uncertainty, right? So this is why we started with probability. So we haven't proven that the true mean is less than 75, right? There's still a 4.6% chance that the true mean is greater than 75, right? So that's about 1 in 20. So we have not proven that the true mean is less than 75. But what we are able to say is that with greater than 95% confidence, we have greater than 95% confidence that the true mean is less than 75. Does that make sense? Okay. Yeah, so this is where we have to start living with and dealing with uncertainty, right, in our results. So in general, we reject the null hypothesis if the p-value is less than alpha. But there are different ways of constructing our tests using this t-distribution depending on what it is that we're really trying to test or what our alternate hypothesis is, right? So we were looking at the alternate hypothesis that the true mean of the population is less than some value mu naught, right? So is the true mean less than 75 kilograms per hour? In that case, we reject the null hypothesis if our t-statistic that we compute from the sample that we actually have is less than negative, the limiting t-statistic, less than negative t alpha. But we can also construct an alternate hypothesis that like let's say we are looking at yield of a process, and we're concerned with, is the yield greater than a certain number, right? In that case, we would test for the mean greater than the null hypothesis mean or some limiting mean. And we're going to then reject the null hypothesis and accept the alternative hypothesis if our t-statistic that we compute from our experiments is greater than the t-statistic at our confidence level. We can also evaluate the hypothesis that the mean, so if our alternative hypothesis is that the mean is just not equal to that number, then we're going to look for a t-value that is outside of the range of t statistics that we compute. In this case, for alpha divided by 2, it'd be a two-tailed t-test. Okay, so we can construct this in different ways. But for example, if we're looking at this, we're trying to evaluate the alternative hypothesis that the true mean is greater than some limit, or alternatively, we can think of this as saying that what is the probability that we observe a certain set of mean values if the true population mean is this mu naught or lower. In that case, it's like if we were up on this curve, we'd be on the right-hand side of this curve instead. And we would be asking, is there a sufficiently low probability of seeing the observed results given that null hypothesis, but from the right-hand side. Okay. We'll do another example of a significance test. So that was an example of significance test based on the t distribution. And you'll see that on your homework, so you can work with that through a worked example. But we looked at other estimates of uncertainty, or other ways of estimating uncertainty in previous lectures. And we can use those estimates of uncertainty to develop significance tests for other situations. So one example that we saw was for the proportion of results within a sample. And so we can, so this is a binary decision, but if we have a binary decision between two results, two outcomes, a true result, a false result, a successful result, a failure result, we know that from lecture 1, lecture 2, we know that we expect to see a binomial distribution. But we said in a previous lecture that if the sample size is large, then we can approximate the binomial distribution by the normal distribution. And we put conditions on that, that the np greater than or equal to 10 and n times 1 minus p greater than or equal to 10. But basically, this is condition that the sample size is large enough that we can approximate binomial by the normal distribution. And so in that case, we can then use that normal distribution to do hypothesis testing about an observed proportion of, in this case, it's going to be voters or votes. So let's say we have an election poll with a random sample of 1,000 voters, and 550 voters prefer one particular candidate. So P, right, the observed proportion is 0.55. So from this result, we want to know the margin of error, and obviously if this is your pollster, your client then wants to know how sure they can be that they're supported by a majority of the voters. So we can start with, so again, we're going to start with calculation of confidence interval, and then we're going to perform a hypothesis test. So we mentioned this in lecture 8, but for a population proportion, the confidence level for a given significance is, again, assuming that we have a population that's large enough that we can use the normal distribution. It's the actual observed proportion, that p hat, plus or minus our z statistic for alpha over 2 times the standard error for p hat, where the standard error was given by this number here. Okay. So this approach applies because np is greater than 10 and n times 1 minus p is also greater than 10. And so the next piece of code computes those results. So we compute margin of error. We find the z statistics using normal distribution. And our end result, so p hat was just 550 over 1,000. So the observed proportion was 0.55. The standard error was 0.015. Our z statistic, 1.96. And so we ended up with a margin of error of 0.03. So in this case, we would say that the, right, so typically in polling results, you might see this reported as a proportion of, or the result is that the probability is 0.55%, or the proportion of voters voting for this particular candidate is 55%, with a 3 percentage point margin of error. Okay. But what we want to know now to get this, to bring it to a hypothesis test, is this evidence that a majority of voters, right, that greater than 50% of voters in the district favor our candidate, right? So to answer this question, again, we're going to be setting up a one-sided hypothesis test, where now we're trying to see, we're evaluating this alternate hypothesis that the proportion of voters in favor of this candidate is greater than 0.5. Right, so that is our hypothesis. And so, sorry. Now I just repeated that thing again. Okay, sorry. I just lost my place for a second there. So our alternate hypothesis is that the proportion of voters in favor of our candidate is greater than 0.5. Our null hypothesis is going to be that the proportion of voters in favor of that candidate is 0.5. And so again, n is large, so we can use the z score as our test statistic. We have the standard error calculated just as above, the z score calculated as shown here. And so that's calculated in the next piece of code. And then we're going to run, so we defined a function here that calculates those statistics, and we run that function. And our result is that the, again, the z statistic now is 3.162. And so the area that we receive, or the p-value that we get, is 7.8 times 10 to the minus 4. We're going to reject the null hypothesis. So because the p-value is less than our significance level, we're going to reject the null hypothesis and therefore accept the claim that the proportion is greater than 0.5. In this case, it's not n greater. So we're using the z statistic because n is large enough. But in this case, it's not n greater than 30. It's np greater than 10 and n times 1 minus p greater than 10. Because remember, this is a binomial process, right? That we have two possible outcomes. Either people favor the candidate or they don't. And so it should be governed by the binomial distribution. But we said that because the number of events is large, and it's large enough, the binomial distribution basically becomes the normal distribution. And so we use the z statistic instead. Does that make sense? And the test for whether or not we can use the normal distribution to approximate the binomial process is not n greater than 30. It's this n times p greater than 10 and n times 1 minus p also greater than 10. Does that make sense? N is greater than 30, yep. So when we're considering the t statistic, so the t statistic is like for continuous distribution of population means, like in the previous example. In that case, if n is greater than 30, we can use the normal. You could also use the t, but you're going to get the same result because they become the same. Okay. Okay. So this is what this test looks like, and I've kind of exaggerated the result here. Apologies again for my hastily drawn sketch, but so what we're doing, so we're evaluating against the null hypothesis that the true population proportion is 0.5, right? So we're computing and we're approximating that using a normal distribution because again, n is large, right? We had a large number of samples in this poll. N times p is greater than 10, definitely, and n times 1 minus p is also much greater than 10. And so normal distribution well approximates the range of observed proportions, right? So this tells us the range of observed proportions we would see if the true population proportion were 0.5. Okay, so it's a normal distribution with a mean of 0.5 and a standard error of that 0.158. or standard deviation of the 0.15b. And then what we look at is for our actual observed proportion of 0.55, apologies if you can't read that, but that says 0.55. We compute the z statistic, and I think it's really somewhere further out here. That z statistic gives us, has a value of 3.1, about 3.1, which corresponds to an area under the curve, or a p-value of 7.8 times 10 to the minus 4. And so as a result, that probability is definitely less than our 0.05 significance level. And so we say that we're going to reject the null hypothesis, right? So the area under the upper tail is much, much less than our significance level of 0.05. So we reject the null hypothesis, and we conclude that a majority of voters do in fact favor our client, right? So from our results, yeah. How does the significance level? So in hypothesis testing, we're making a yes/no decision. Do we accept the alternate hypothesis, right, or not? And so whenever we're doing that, we want to say what is the level of certainty with which we want to say that we accept that result? And so ahead of time, before you even do the test, you should set out what is your acceptable level of uncertainty in this result. And so and that is defined as our, right, what significance level we want to see, right? And so from that, we compute in this case, we would compute the z statistic corresponding to that level of significance that we say going into the test is our minimum level of significance, right, for accepting this result. And then we go in and compute in this case, the z-score for our actual observed proportion. And we're looking to see, is our observed z-score, in this case, greater than the z-score that we came into the test saying it had to be greater than? Does that make sense? So, yeah, okay. So that's why. So it's a way of also avoiding some bias in statistical testing, right? We say from the outset, we're only going to accept the results if the uncertainty is within some prescribed limit. Often we set that limit to 0.05, but again, that means it's about a 1 in 20 chance of there being an error. So in some cases, this may not be close to a low enough significance, and we'd have to use something that's much further out. Yeah.
So what you're going to do is you're going to be able to calculate
what's to stop you from sampling until you get the number you want? Yeah, that gets into ethics of statistics, honestly. So what you described is sometimes called p-hacking, and it's a problem in science and polling. So the thing to stop you from doing that is ethics. Doing that will essentially invalidate this test. If you only measure results until you get a result that you want, and you stop then you are much more prone. And this p-value no longer really describes your actual probability of observing that result. So this assumes that you have a random sample, and in some sense, your sampling is no longer random at that point. This is a major problem. So there's sometimes called a crisis of reproducibility in social sciences. One of the contributing factors to that is that it was common practice until maybe less than 10 years ago to run some social science experiment. Like get college students in Psych 101 and ask them to do some survey result or something and see if hearing about the consequences of your actions in some lecture on day 0 affects how charitable you are over the next several days or something. Let's say initially you say you're going to run that experiment for 5 days. And then after 3 days, you look like you see that you're getting results that look good. You stop the experiment then. That's bad. Okay, that can lead to erroneous results. This p-value no longer really applies. And so there's a big reckoning in that field actually right now based on that. And this is why in clinical trials, for example, right, this could obviously be a problem because the people running the clinical trials, typically the drug companies, have a vested interest in making sure that the results support the use of their drug, right? So one way that we attempt to safeguard against that is by requiring that all trials are registered. So you can go online, there's a registry for clinical trials, and you can find which trials are currently ongoing, how many people have they enrolled. You can't see the results until the end, they're blinded until the end, but they all have to be registered through a government portal. And it's done that way so that the trial is designed to achieve a certain level of significance if the outcome is really true, if they're going to see the effect that they actually expect to see. But they are required to run the trial for the amount of time or number of patients specified at the outset. They're not allowed to stop it when they just get to a result that they want. But yeah, that's one way that statistics can be misused. Right, so in this example, your pollster, right, if I'm a pollster for a particular client, that client obviously wants evidence that they're going to win the election. And so if instead of sampling 1,000 people, which is what I knew I had to do from the outset or how I designed the poll at the outset, I just stop when I get to a proportion that's statistically significantly greater than 0.5, then, I don't know, my client should probably fire me if I'm doing that. But it does happen, and it happens all the time. It's something to watch out for. Okay. So another example, again related to sampling on the population mean. In this case, we're going to look at an example where our n is 49. So we're sampling about population mean. So when we have a sample, or when we're looking at probabilities related to population mean, what distribution do we use? So we have samples about population mean. What is the distribution that describes the range of observed population means? So what distribution? So we've looked at a few different PDFs, for example. So the exponential distribution describes the range of expected results, or the proportion, the probability of expected results for the time duration between independent events, right? That's the exponential. In this case, let's say I'm looking at the proportion of population means, so the probability of getting a certain mean result from a sample. What is the statistic that describes, or the distribution that describes population means, observed population means?
Normal.
Under what conditions is it normal?
We have more than 30 means. That's normal.
So in general, it's the t statistic, or the t distribution describes the probability distribution of seeing a given population mean value. When n is greater than 30, then we use the normal, because the t statistic becomes the normal for n greater than 30. In this case, n is 49. So can we use the normal distribution with n is 49? Yes. With n is 49, and when we're looking at the proportion of population means, then yes, we can use the normal distribution. We want to know if certain boxes of granola contain at least 16 ounces of cereal. So our alternate hypothesis is and we want to know if we should be rejecting these samples. So we're going to set this up with our alternate hypothesis of mean less than 16 ounces. The null hypothesis is again going to be equal to that the actual mean is equal to 16 ounces. And we're going to be using, because our n is greater than 30, we're going to be using the z-score, because the t distribution is the same as the normal distribution for this number of degrees of freedom, 48 degrees of freedom. Um, so let's say in our testing, we find that the sample mean is 15.9. The sample standard deviation is 0.35. So can this company that's trying to accept these or trying to evaluate these cereal boxes, can they claim that the weights are significantly light using a significance level of alpha of 0.05? So again, we're going to put in our observed results, compute our z statistic for those observed results, and in this case, we're just finding the area. So we're finding the p-value that corresponds to that observed z statistic. Yep. Yeah, I mean, in this case, it's convenient to use the alternate hypothesis as the mean less than 16 ounces because my observed sample value was less than 16 ounces. Probably should have reordered that. My observed value is less than 16 ounces. So really, I want to know if the true mean is less than 16 ounces. Yeah, then it would be more convenient to do the greater than. Yeah, that's correct. Yeah. And so we're gonna, and then so this is our definition of the of our function, and we end up with a p-value of 2.7 times 10 to the minus 2. And so we would, right, so this p-value is definitely much level. Let's say we're doing this to a significance of 0.05. We see that this p-value is much less than 0.05. And so therefore we would reject the null hypothesis. In this case, Wholly Foods rejects the null hypothesis and the granola, right? So both are rejected in this case. So in summary, we had this question of how we select the null hypothesis, right, which is just our question from the class. So in this case, we observed a mean of 15.9, and our goal was to establish the assertion that the boxes were underweight, right? So I'm a company that I set this limit of 16 ounces. I observe a sample mean of 15.9. I want to know how likely is it that the actual population mean is less than 16. Right, my average was less than 16. How likely is it that the true population mean is also less than 16? So that becomes the alternative hypothesis in my problem. So HA is the alternative hypothesis. It's typically the claim that we want to establish. The null hypothesis is the denial of that claim. It's the thing that we're trying to argue against. There are different types of errors, and we'll go into more detail on this in future lectures, but what we call a type 1 error is the rejection of the null hypothesis when the null hypothesis is actually true. This is also called alpha. It's actually why it's alpha, because it's a type 1 error. So alpha is the probability of making a type 1 error. It's also called the level of significance. So again, if our alpha is 0.05, which is often the level of significance that we choose, then we have about a 1 in 20 chance of making a type 1 error, a 1 in 20 chance of rejecting the null hypothesis when the null hypothesis is actually true. A type 2 error is a failure to reject the null hypothesis when the alternative hypothesis is true, and that's called beta. For the type 2 error, and we'll talk more about that in the future. Okay, there's another example here on small sample size and tests of significance for population mean that is using the t statistic, and that I will refer you to in the notes, right? So this is in the notes for lecture 9, but it follows through very similar reasoning to what we've been looking at so far, okay? I do want to quickly talk about, or at least introduce this concept of uncertainty analysis and propagation of uncertainty. There's a bit of a derivation that we're not going to go through in detail, but I do want to share the main result with you. And we'll review it at the beginning of lecture on Wednesday, but I just want to get this out so that we can keep moving forward. Any questions on hypothesis testing? Any more questions on hypothesis testing? Yeah. Yeah. Yep. We came to the conclusion the girl was underweight. Yeah. Yeah. There was so we rejected the null hypothesis, and we said that there was a very low probability of seeing a sample mean of 15.9 to that degree of confidence if the true sample mean was actually 16 or greater. So we rejected the null hypothesis. That's correct. Yep. Okay, so just when we have, so we've talked about how we can compute uncertainties from experimental results, right? So we can make, for example, 95% confidence intervals on the observed, on the population mean from our sample mean. It's often the case, though, in engineering that we're trying to, our actual, like the actual results of a process is based on the combination of a number of different measured variables. And so we can, if we know the uncertainty in all of the inputs, we can estimate the uncertainty on what the output is. And we've seen this already. So in our, I believe it was lecture 1, we said that we had a linear combination of, if our output, let's say y, is a linear combination of some random variables x with some coefficients a, then we said that, for example, we can write the variance of that variable y as a squared times variance of x1 plus a2 squared times variance of x2, and so on, right? And so we've seen this before. We saw this on quiz 1. It was also on quiz 2. So we can go further than this. So if we have a function which is not just a linear combination of variables, we can approximate the uncertainty or let's say the standard deviation of the resulting value, or of the resulting function value, sigma f, using this expression here. So, and this is based on the partial derivatives of the function with respect to each variable f, each variable. So in this case, partial f, partial x squared times sigma squared x, partial f, partial y squared times sigma squared y, partial f, partial z squared times sigma squared z, where f is a function of x, y, and z. And this is based on Taylor series expansion. So, so if we have uncertainties, we can do the same thing where we just use, instead of sigma, we put in the uncertainties that we have in the measured values. And we can then use this to propagate our uncertainties. So we use the same expression to propagate our uncertainties. So for example, it could be based on our 95% confidence intervals. So in general, we could then write the uncertainty squared in our function value. It's just the sum of the partial derivatives times the uncertainty of each one of those variables squared. So this allows us to propagate uncertainties through some known function. And we'll see it's often convenient to work with fractional values where we normalize by the mean. And we will pick up on Wednesday with an example where we're going to apply that with our function. So a given function here, again, this is a nonlinear function now, where we're looking at the velocity of an airstream based on some other values. And we'll see how we can propagate uncertainties in these values through to what the expected uncertainty is in this velocity of the airstream. Okay. All right, so we'll pick up there on Wednesday. Any other questions before we break? Okay, thank you all.